Today we're going to, this is Electric Universe Geology Earth News. Today we're going to talk about cinder cones. This one is close to Flagstaff, just northwest of the town of Flagstaff. This is a special one. This has a missing area right here. Normally a cinder cone would have vents right here, and the wind, in this instance, would have been blowing this way, towards the north, what would that be, northeast. So you don't get any accumulation back here because the wind is blowing it away. It's making a U shape. Many cinder cones are U-shaped. But this one has this missing piece. Let's look at it in satellite real quick. You can see the dirt that's missing where your vegetation is not growing any longer. Back to terrain. So let's zoom out. Get a feel for the neighborhood. You see all these cinder cones, many of them U-shaped. U's. It gives you the direction of the wind at the time the cinders were blowing out of it. And here we have Flagstaff. Humphreys Peak, San Francisco Mountains, I believe they're called. I have a vision for this area. Actually, let's zoom out a little bit extra so we can see the Grand Canyon, which is up here. This is a high point. This goes up well over 8,000 feet. This is a high point. Everything surrounding it is much lower. A lot of limestone. Everybody seems to agree it was an inland ocean at one time. So you have an ocean sticking up. You have these mountains sticking up above an ocean. And my thinking is, which might be delusional, that electricity is trying to go to ground. And oceans don't get a lot of lightning. You don't have a lot of grounding over the ocean. It seems as if the water's an insulator. And I'm guessing this rock would be a better insulator than fresh, salty mud. So if you have a salt water ocean that used to come right to the edge of this mountain, and it's the reason the mountain is that shape, that's why the mountain grew to the edge. It's where the water prevented accumulation. Anything sticking up above the water grew. So that's why the mountain is this shape. So surrounding it, you're going to have wet, salty mud. To me, that's an area that's going to be really prone to grounding. Thunderbolts going to ground, creating telluric currents. The telluric currents possibly heating the ground to the point where cinders start spewing out from under the ground. And if the process gets even more energetic, the current density increases, you wind up with basalt flowing from the bottom of the cinder cone. There's basalt flowing from here. I think it's Sunset Crater. That's Sunset Crater Volcano National Monument. There's all kinds of basalt coming out of it. You can see where the basalt starts from. You can see it goes downhill. It's blocky. It's ropey. It's an obvious flow, as opposed to the things that I see on mesas and cap rocks that look nothing like a basalt flow. So this is our friend up here. Now we're going to look at it. Just a few more minutes with the map here. Here's the road that comes off of 180. There's a little parking lot here. You got to walk. It's, I guess, close to a mile, a little less. And you walk right through here, which I think is a drainage. This area was big enough to have enough water draining out of it that this is prevented. I have a photograph I'll show you in just a moment. And then you walk up through here, with cinders over here, cinders here, there's more here. And then you see the vents right here with the wind blowing this way. So I think this formation is from these vents. This formation is from these. I'm going to have shots that show this area later, where the wind is blowing down this way. This ripped off this side, so you'll be able to see the inside of the cinder cone, which is normally not visible. Now let's go to the photographs. This is the trail that leads in to the vents. Here's the cinders that were blowing, I think, downwind going to the northeast. Gives you some idea of what it was like. Here we have some vents. This is where the cinders are coming out so hot it's molten. But as they blow downwind, they're no longer molten. After, it looks like 20, 30, 40 feet, they're cooling off because there's air surrounding each little bit of dust, cinders, and they cool off really quickly in the air. But these look so gnarly and burnt and black and melted. This doesn't look like it's eroded very much. This is the kind of thing that geologists claim evaporates when there's missing basalt, missing volcanoes. It's the vents that go away. The basalt's there, but the vents that allegedly the basalt came from are gone. This is going to be the last place in the world to erode, not the first. This has got a certain funk to it. You can see the different colors. I don't know why there's different colors. This looks like it was hotter, but I don't really know. The bubbles are interesting. Could be heat, could be electricity. I was fascinated with these things when I first started my geologic adventure years ago, but I've found other things more interesting since. But this isn't something that's going to erode real quickly. Another similar angle. I pumped up the color a little bit, excuse me. But yeah, you can see the burnt areas. You can see where the cinders were coming out, creating these formations. This is the shot I mentioned earlier. These are all the cooled off cinders that have cooled off. The vents are just over this ridge, so in that distance you no longer have molten funky rock, but you have these cinders that are blowing downwind. This was probably all solid at one time. The new vents that I think ripped this out are down here, the ones that we've been looking at that are also melty and black looking. So this is something that normally people don't get to see. The cinders that were ripped out by the new vents, if that is true. So my basic premise is that these are arc discharges, creating telluric currents, possibly going underground, heating the ground, making cinders. If it gets really hot, you wind up with a basalt flow coming out of it. It's an electrical explanation for cinder cones and volcanic material. Thank you very much.